Welcome everyone. Today we are going to explore one of the most mind-bending ideas in all of science, black holes, and how they actually bend space and time itself. Not metaphorically. Not as a figure of speech. Literally. Imagine you are holding a stretched rubber sheet flat in front of you. Now imagine placing a very heavy bowling ball in the middle of it. The sheet sinks down around the ball, creating a deep curve. That curve is exactly how scientists describe what a massive object does to the fabric of space around it. This is not just a pretty picture. It is the foundation of how our universe actually works. And black holes take this idea to an extreme that is almost impossible to believe. So let us start at the beginning. What exactly is a black hole? A black hole is a region in space where gravity is so incredibly strong that nothing, not even light, can escape from it. It forms when a very massive star reaches the end of its life and collapses under its own weight. The star crushes itself into an incredibly small, incredibly dense point called a singularity. Think of it this way. Imagine taking the entire mass of our Sun, a ball of gas so large that 1 million Earths could fit inside it, and squeezing it down to the size of a small city. The gravity produced by that compressed mass would be so powerful that it would warp everything around it. Now, black holes that form from dying stars are even more extreme than that. Some black holes contain the mass of millions or even billions of suns, all packed into a single point. The gravity they produce is almost beyond human imagination. But here is where things get truly interesting. Black holes do not just pull objects toward them like a vacuum cleaner. They actually change the shape of space itself. To understand this, we need to talk about a man named Albert Einstein. In 1915, Einstein published his general theory of relativity. This was one of the greatest scientific achievements in human history. And at its heart was a revolutionary idea. Einstein said that space and time are not separate things. They are woven together into a single fabric called spacetime. And massive objects, like stars, planets, and black holes, do not just sit inside this fabric. They bend it, curve it, and reshape it. Go back to our rubber sheet analogy. When you place that heavy bowling ball on the sheet, smaller objects nearby will roll toward it along the curved surface. They are not being pulled by an invisible force. They are simply following the shape of the space around them. This is what gravity actually is, according to Einstein. It is not a mysterious pulling force sent out across empty space. It is the curvature of spacetime caused by mass. Now, a black hole creates the most extreme curvature possible. The rubber sheet does not just dip, it tears completely through. The curve becomes infinite at the singularity. And this creates effects that seem completely impossible. Let us talk about the event horizon. This is the boundary around a black hole, the point of no return. If you cross the event horizon, you cannot escape, no matter how fast you travel. Even light, which moves at 300,000 kilometers per second, cannot escape once it crosses this line. This is why black holes are black. No light comes out. They are invisible against the darkness of space, unless we look for the effects they have on everything around them. Now here comes the part that truly bends the mind. Black holes do not just bend space. They also bend time. Einstein's equations showed something extraordinary. The stronger the gravitational field, the slower time passes. This is called gravitational time dilation. And it is not a theoretical idea, it is a measured, confirmed fact of our universe. Let us use an analogy to make this clear. Imagine two friends, let us call them Maya and Carlos. Maya stays on Earth. Carlos travels to a point very close to a black hole and hovers there for what feels to him like 1 year. When Carlos returns to Earth, he discovers that 10 years have passed for Maya. Carlos has aged only 1 year, but Maya has aged 10. This is not science fiction. This is real physics. Time actually moves more slowly in stronger gravitational fields. In fact, you experience a tiny version of this effect every single day without knowing it. The GPS satellites that power the maps on your phone orbit high above Earth, where gravity is slightly weaker. Time passes very slightly faster for those satellites than it does for us on the ground. If scientists did not correct for this difference, your GPS would give you wrong directions. The error would grow by about 11 kilometers every single day. The fact that your phone navigation works accurately is direct proof that Einstein was right about time dilation. But near a black hole, the effect is not tiny. It is enormous. If you could hover just outside the event horizon of a massive black hole, time would slow down so dramatically that a single hour for you might equal thousands of years passing on Earth. You would be, in a very real sense, traveling into the future. But here is what almost no one talks about. Black holes do not just bend time for things near them. They also bend the path of light itself. Light always travels in a straight line, or so we think. But remember, black holes curve the fabric of spacetime. And when spacetime is curved, the straightest possible path through it is also curved. So light bends as it travels near a massive object. This effect is called gravitational lensing. And it creates some of the most beautiful and strange phenomena in the universe. Imagine a galaxy sitting directly behind a black hole from our point of view. Normally, we would not be able to see that galaxy, the black hole would be in the way. But the black hole's gravity bends the light from that distant galaxy around itself, like a lens made of pure gravity. The light curves around both sides of the black hole and reaches our telescopes. The result is that we see the distant galaxy as a ring of light surrounding the black hole. Astronomers call this an Einstein ring. It is one of the most spectacular sights in the cosmos, and it only exists because massive objects bend the path of light. We have actually photographed this effect. In 2019, scientists released the first ever direct image of a black hole, the supermassive black hole at the center of a galaxy called M87. The glowing orange ring of light you may have seen in that famous photograph is not the black hole itself. It is the light from hot gas being bent around the black hole by its immense gravity. That image was not just beautiful. It was confirmation of Einstein's predictions, made over 100 years earlier, using only mathematics and imagination. Now let us go even deeper. What would actually happen if you fell into a black hole? From the outside, something very strange would appear to occur. Remember that time slows down near a black hole. So if you were watching someone fall toward the event horizon, you would see them slow down more and more as they approached it. Their image would become redder and dimmer as the light from them lost energy fighting against the gravity. Eventually, they would appear to freeze completely at the event horizon, suspended there forever, from your point of view. You would never actually see them cross it. But from the perspective of the person falling in, they would cross the event horizon without even noticing a clear boundary. They would simply fall through. The laws of physics would still work normally around them, at least for a moment. Beyond the event horizon, however, the future is not in front of you. It is below you. The singularity is not a place in space, it is a moment in time. And just as you cannot avoid moving forward through time in ordinary life, inside a black hole you cannot avoid moving toward the singularity. It is your inevitable future. This is one of the most mind-bending ideas in all of physics. Inside a black hole, the directions of space and time swap roles. Moving through space becomes unavoidable in the direction of the singularity, just as moving through time is unavoidable for us right now. Scientists are still working to understand what happens at the singularity itself. The mathematics breaks down there, it produces infinities, which usually means our current theories are incomplete. This is one of the great unsolved mysteries of modern physics. To truly understand the singularity, we will need a new theory that combines Einstein's general relativity with quantum mechanics, the science of the very small. This search for a unified theory is one of the biggest goals in all of science today. And now, let us talk about why any of this matters for our everyday lives and our future. At first, black holes might seem like distant curiosities, extreme objects far away in space that have nothing to do with us. But the science of black holes has already changed our world in practical ways. The GPS example we mentioned is just the beginning. The deep understanding of spacetime that came from studying extreme gravity has shaped our entire framework of modern physics. Technologies built on this understanding include medical imaging, laser systems, and the atomic clocks that keep our global communications synchronized. Looking forward, understanding black holes may be the key to some of the greatest discoveries of the coming centuries. Scientists believe that studying the edges of black holes could reveal the long-sought connection between Einstein's theory of gravity and quantum mechanics. That connection, if we find it, could unlock entirely new forms of energy, new ways of understanding the origin of the universe, and perhaps even new ways of thinking about the nature of time itself. There is also something deeply philosophical here. Black holes force us to confront the fact that time is not fixed. It is not a steady river flowing at the same rate for everyone everywhere. Time is flexible. It stretches and compresses depending on gravity and speed. The universe is far stranger and more beautiful than our everyday experience suggests. Every time you look up at the night sky and see a star, you are looking at an object that bends spacetime around it, just a little. Our own sun bends spacetime enough that scientists have measured it precisely. The Earth itself bends spacetime, which is why objects fall to the ground. Gravity, as you now know, is not a force sent across empty space. It is the shape of the universe itself, responding to the presence of mass. And black holes are simply the most extreme version of this universal truth. So the next time you hear about a black hole, remember this. It is not just a place where things disappear. It is a place where the fabric of reality is stretched to its absolute limit. Where time slows to a crawl. Where light bends in great arcs around an invisible point. Where the future is not ahead of you, it is below you. Black holes are the universe showing us its most extreme face. And every time we study them, we learn something new about the nature of space, time, and existence itself. Is it possible that somewhere in the universe, a civilization has learned to use the time-bending effects of a black hole, to travel into the future, to preserve knowledge across vast stretches of time, or to solve problems that would take millions of years to compute? We do not know. But the physics says it is not forbidden. And that, perhaps, is the most exciting thought of all.